Can you hear me? Can you hear me?
Okay. You ready?
Yes, can you hear me? Shall I go ahead?
Go ahead.
Okay. So good morning, everyone. Today I would like to talk to you about scientific realism and the dark sector, so dark matter and dark energy. In the standard model of cosmology, all the matter we're familiar with that we know and love turns out to be only a small percentage of the total energy content of the universe. A much bigger chunk is dark matter, and an even bigger chunk is dark energy. And of course, the million-dollar question is what these two entities, things, stuff are. Now, a lot has been written about scientific realism. For today, all I want to talk about is very minimal claim or necessary condition on scientific realism. I claim that if you come to me and say I'm a scientific realist about some unobservable, some theoretical term, then I think you should be able to tell me at least roughly what that term is, right? For me to know what this thing is that you're supposedly a scientific realist about. And the whole claim of this talk is that dark matter, and then towards the end I'll also say a bit about dark energy, currently does not seem to satisfy even this minimal necessary criterion for scientific realism, right? So I think as of right now, and this might change tomorrow, if someone says I'm a scientific realist about dark matter, then I don't think that claim is precise enough semantically for it to be clear what that means. Just to be clear, I'm not saying we have evidence that there's no dark matter. I'm just saying that the right epistemic attitude is one of agnosticism. Okay, so as I said, I will mostly focus on dark matter for the first part of the talk, and towards the end I'll say a bit about dark energy, which is subtly different. Okay, so dark matter. Well, it turns out, and what is well known, is that if you just use GR and luminous matter, then you're going to get the wrong answers if you want to predict how the luminous matter is going to behave. And the discrepancies pop up at basically all relevant scales, right? So at galaxies, but also galaxy clusters, and even at the largest cosmological scale. Right? So those two ingredients by themselves cannot be the whole story. So either we need something more, some more matter, but we don't see it, so dark matter, or we need to enhance, boost gravity in a certain appropriate regime. Now, the point is not that we have no clue what dark matter might be, right? So, for instance, one of the mainstream candidates is a WIMP, weakly interactive massive particle. And if we would know for certain, oh, this is the dark matter in our universe, then I think it will be relatively clear what it will mean to be a realist about something like this, right? Or at least as clear what it will mean to be a realist about an electron, right? So if, for instance, it would be a specific model of a WIMP, and you might know, for instance, that it has zero hypercharge, a specific mass, a specific annihilation cross-section, and that it does or doesn't have further self-interactions, and also that there's a cosmic density of 27% of the total cosmic mass energy budget. Right? If this is what you would know, then okay, sure. If you're a realist about electrons, then you should also be a realist about dark matter. However, the problem here, as I said, is not that we have no clue what dark matter is, but just that there are way too many options on the table. So here that's illustrated by a cartoon, right? The whole cornucopia, a myriad of different options on the table. And here kind of the same point is being made in a different infographic. And now you might think, well, okay, the only thing where all these options differ by their mass differs by where the range is 90 orders of magnitude, but still you might say, well, the only thing we don't know is the mass parameter. I mean, we still know that there's dark matter, we just don't know the value of one thing, its mass, and what gives. However, the problem is that it's not just that all these things are kind of the same type of entities and they just differ in mass, but they're radically different entities, right? So, yeah. The thing they have in common is quite weak. So, for instance, right, some of these things here on the table here are proper point particles, you might say, or close to being a point particles. But fuzzy dark matter, for instance, has a de Broglie wavelength of a whole kiloparsec, right, the size of a dwarf galaxy. So that's a totally different thing. Black holes, maybe it's not even a form of matter, maybe it's modification of gravity. So these are radically different things, ontologically speaking. So it's not just that we don't know the value of one parameter, its mass. No, these are very different things ontologically that are on the table. And of course, the big elephant in the room is that empirically speaking, we haven't narrowed it down to one of these options. Some of the ones on the previous slide are mainstream, others are not. But the point is that even within the mainstream candidates, because we haven't, for instance, found one at direct detection experiments or at the LHC, there's so many options on the table. And the point is that what they have in common, right? If they would all be roughly the same, okay. But the point is that what they have in common is very, very weak. So even if you would only look at what many people would say is the mainstream candidates like WIMPs and axions, then you end up with a quite thin common core concept of dark matter, right? Something like this. A massive field with a contribution to the total cosmic mass energy budget of 27%, thereby being responsible for certain gravity-mediated observables related to structure formation, clusters, and galaxies, which I showed a few slides ago. And if it's a particle, which it doesn't even have to be, its mass is roughly between 10 to the minus 22nd for fuzzy dark matter, or all the way up to 10 to the 13th EV for WIMPzillas. Right, so this is already quite thin. But if you are a bit more liberal in what you allow as options that are on the table, then things get even more thin, right? Then it's basically stuff, right? You don't even know for certain it's matter. Maybe it's a modification of the gravitational field. And it's stuff that either contributes 27% to the total cosmic mass energy budget, or acts as if it does so, and thereby being responsible for these observables, which are all gravity mediated, right? We haven't even necessarily detected that it's a form of matter, because all our evidence is gravity mediated. Right, so one might say, and this is how Aguiar says it, that the label dark matter, right, the common core of all these options on the table, just encapsulates our ignorance regarding the nature of most of the matter in the universe. Right, so basically, what I have in mind here is that, sure, if it were one of these very specific options on the table, like a WIMP or some specific action model, then, right, a very thick concept like an electron, then it would be clear, I think, what it would mean to be a realist about it. But the point is, and there might be other examples which are somewhere in a gray area, and I don't have anything to say about it. I wouldn't know how we would go about judging those cases. But I think the point is, for dark matter, we're so far from the perfect case, regardless of whether you commit to the thin common core or even go to the thinnest common core. I think this whole range, it's not clear enough what it means to be a realist, right? You're just saying something like, I'm a realist about, and then a whole disjunction of either some fuzzy dark matter or a black hole or WIMPzilla or something else, or maybe modification of gravity. And that, I would say, is just too vague. Right, so let me just make kind of the same point in different words. This is one way, by Anjan Chakravarty and others, how you might think of realism, or really the spectrum of versions of realism and anti-realism. Chakravarty says there are basically three questions that you need to ask yourself in order. If you say yes to all of them, you're a realist, and depending on whether you say no immediately, then you're a hardcore realist, or if you say no at a later stage, you're kind of an intermediate, weak anti-realist. And so the first question you are asked is the metaphysical component. Do you believe in some mind-independent world, right? Do we live in the matrix or not? Some people get off the boat there, hardcore anti-realist. If you think, okay, sure, we live in a mind-independent, there is a mind-independent reality, external reality, then you get asked the second question. That's the semantic component. And typically that's phrased as, when scientists talk about unobservables like electrons or coronaviruses or dark matter, should we construe these terms in a literal sense? Are they really talking about little particles or little crown-shaped viruses? And some people, right, famously or infamously, the logical empiricists would say, well, no. When scientists talk about electrons, it's not some tiny particle. That's more metaphorical, or it's really a shortcut for some complicated laboratory procedure. For instance, about setting a bubble chamber in such and such settings and observing such and such a bubble track. That's what we mean by electron, but electron is not literally a little particle. And some people would say, yes, no, when scientists talk about these unobservables, they really literally talk about little viruses or little particles or strings. And then you get asked the final question, the epistemological question, basically, are you optimistic or pessimistic that scientists will find out the truth about these statements about unobservables, right? And that's where the last stage where anti-realists can get off the boat, right? Bas van Fraassen with the constructive empiricism. Realists will say, no, yes, there's a mind-independent external world. Scientists really mean literally what they say. and we have found out the truth, or we are going to find out the truth about statements about such unobservables. Now, for dark matter, the problem here, I think, is this middle component, the semantic component, right? So as I said, typically that question is phrased as, should we take scientists literally when they talk about certain concepts? But I would say there's even a prior question that, right? That's whether a certain concept, in this case dark matter, is even clear enough, right? If it's not too vague, to even know what it means to say, oh yes, they literally talk about such and such a thing. And I think that's the whole problem with dark matter, or at least the Common Core of all the options on the table, that it's so vague that I don't even know what a physicist is telling me if they say they believe literally in that concept, other than that they believe literally in some big disjunction of radically different things it could be, right? So I think what this also shows us is that perhaps we shouldn't think of the realism spectrum the way Chakravarti did and make a slight modification. I think the semantic components and the epistemological components kind of come apart. They're two different dimensions, independent from each other. So my point here is that I think for dark matter, we should not yet, as of right now, be semantic realists, right? The concept is too vague. But that does not imply, that doesn't mean I don't get asked the final question, right? I think what I just said is combinable with either being an optimist or pessimist, that tomorrow the empirical situation will change. For instance, at LHC, they might find something, or they see on experiments, such that at the same time, the concept of dark matter narrows much more, and we have found out which of these concepts, which of these statements is true. So I think this semantic agnosticism is compatible with whatever you think about the epistemological component. So let me just contrast my view with some other famous or infamous views. Right, Hacking has notoriously, but he said, well, if you want to be realist, you need to be able to do experiments. In astronomy and in cosmology, we can't ever do any experiments, so we should be anti-realist about everything in the universe that's not on Earth. Well, this is a very generic argument about everything in astronomy. My claim here is really only about dark matter, and in the second about dark energy. So that's how I differ from Hacking. The logical empiricists, as I said, they have very strong a priori arguments, universal arguments based on the verification principle of meaning. They would say just the nature of such things, of everything that's not directly observable, is such that we cannot be realist about it. But the claim I'm making here is very different in the sense that it only applies to dark matter because of the current, right, it's naturalist, because of the current empirical situation. And it might also change tomorrow if the empirical situation changes tomorrow, whereas the logical empiricists, the arguments would still be the same tomorrow. Thirdly, Eugene Feinberg wrote a recent paper where they claim that the common core of dark matter is not too thin. I think it is, but Feinberg thinks that's not the case. Feinberg thinks it constitutes a unique natural kind, right? So that you can already be selective semantic realist. Moreover, this natural kind has already been empirically confirmed. Even though we haven't confirmed the particle nature of dark matter, this natural kind, right, this kind of broad concept that the cosmologists use, that Feinberg claims has already been confirmed. I disagree. I think the common core is so vague. It's a disjunction of all these possible natural kinds, right? Whether it's a primordial black hole or a Wimsilla or some fuzzy dark matter wave-ish thing. And I just don't see how a disjunction of natural kinds can itself be a natural kind. It doesn't carve nature at its joints. And then finally, Simon Altsen and Stathis Psilos talk about kind of inference to the best explanation argument for realism, but this is really about epistemological realism. And my point is really a prior issue, right? The question should first be, are we all clear enough what we mean when we talk about dark matter before you can then come up with explanatory arguments about whether we're going to find out the truth about dark matter. So I think what I say is compatible with, but orthogonal to what they say. So this is my conclusion regarding dark matter. In light of the current empirical evidence, which allows for a cornucopia of radically distinct dark matter models, it's too early to be a semantic realist about dark matter and a fortiori a full-blown scientific realist. And I want to be very clear here. What I'm advocating here is kind of a not yet realism, some kind of agnosticism, right? I'm not saying, when I say anti-realism, I don't mean that we have evidence that dark matter does not exist, right? By that, maybe I should have used the term agnosticism. That's really what I'm saying here, that the correct attitude here is one of agnosticism, and you might combine it with epistemological optimism or pessimism about whether we narrow down this concept tomorrow and find out the truth. And now I have planned to talk a bit about dark energy. Do you want me to continue for a few minutes, or I'm also happy to stop here because I see I'm at 20 minutes. But I think we also started a bit late. Okay, if nobody stops me, I will talk for a few more minutes. Okay, so then dark energy, the situation is somewhat similar, right? So dark energy is that stuff, whatever it is, that is responsible for the observed accelerated expansion of our universe. So there's a whole bunch of options on the table. I've listed them here. I won't go through them all. And again, the situation is similar in that the common core of all these things is very weak, right? We don't even know if it's matter or gravity, space-time, etc. However, one thing you might say here, which is different from the dark matter case, is that if we ignore the recent DAISY results and stick to our current standard model, lambda CDM, where dark energy is the simplest thing it could be, a constant of nature, then you might say, well, that's just the end of it, right? It could well be that there's no underlying microphysics. For the dark matter case, we knew, right? It was kind of a known unknown. We knew there must be underlying microphysics. We just didn't know, we still don't know what of these underlying options it is. For dark energy, it could well just be the case that the cosmological constant is the end of the story, right? There's definitely no logical problem with that being the case. Nonetheless, you might think even if dark energy is a constant of nature, it still seems to be a weird kind of or tricky thing to get a hold of, in the sense that it seems to be a bit matter, a bit space-time, but also a bit constant of nature. And if you can't even classify it according to these most primary conceptual, metaphysical, ontological categorizations, what have you really told me when you've told me that the cosmological constant is responsible for the accelerated expansion of our universe, right? So we talk about lambda as the intrinsic energy of space-time. But energy is typically the essence of something being matter. So it's like the intrinsic material aspect of space-time. So it already falls in both of these categories. Lambda solutions to GR, we typically talk about vacuum solutions. So then it sounds like it's just space-time. And then there are a few other things which I'll skip over in the interest of time. But the point is that even in the simple model of dark energy, cosmological constant, it's kind of a bit like a constant, a bit like matter, a bit like space-time, all at the same time. Right, so this is basically encapsulated in some of these quotes. Have you really given a kind of metaphysical explanation, or have you just parameterized our discrepancies from a model without any dark energy? Right, so Newman says dark energy is really just a name for our ignorance. Turner, a proxy for the real explanation. And even Peebles himself, it's a poor disguise for a fudge factor that we accept because it serves to unify theory and observations so well. So, yeah. The dark energy situation is somewhat similar to dark matter. The common core is quite vague. However, in this case, it could just be the final word if we ignore the recent DAISY results, and the dust still has to clear. However boring that might be, and whereas in the dark matter case, we know there must be some underlying metaphysics. So basically what I'm saying is for the dark energy case, I'm a little more on the fence as to whether one should be a realist or an agnosticist, and I'm very curious to hear what you think on this matter. Thank you for your attention.
Okay. Thanks, Niels. Questions? Time? Minutes? Okay. Yeah.
Hello. Let me ask a question about the composition of dark matter. Do you think that a part of the common core of the conception of dark matter is that it's made of particles? Because I think we don't even know that. Perhaps if dark matter exists, it's not composed of particles, either neutrinos or very known particles or exotic particles, because it's some kind of continuous stuff which oblige us to revise our models of what matter is composed of.
Yes, no, I think I sympathize with what you're saying. And so some physicists are quite strict on what options they think they're on the table. Right, but even then, well, okay. First of all, there's the question: are there in QFT any particles at all? Right, that's a whole debate in philosophy of QFT, which I don't have anything particular to say about, but I am somewhat skeptical that there's a clear notion of particles in QFT. But specifically in this case, indeed, right? If you talk about fuzzy dark matter, which, as I said, this has the Broglie wavelengths, kind of a quantum wave spread out over 1 kiloparsec, right? To call that a particle, I mean, only in some very weak sense. And then I myself, although I see lots of problems with modified gravity, I also see some of its strength. So I think it's not totally ruled out that, or well, like conceptually speaking, and I have a paper on this with Dennis Leemke, we think, well, it's not clear that there's even a clear conceptual distinction between whether you call something matter, particle or not, and whether you call it a modification of gravity or space-time. So in cases like superfluid dark matter, it seems to be a bit of both. So indeed, that feeds into what you're saying, like it's not, we call it dark matter, and that name already seems to suggest a specific answer to the dark discrepancy problem, if you want to have a more neutral name. So yeah, I think we have not figured that out yet. It would be nice if the LHC or direct experiments had figured that out, but we haven't. So I think we should be open-minded and consider kind of hybrid theories where it's maybe a bit of both. Yeah.
Thank you. More questions?
Yes, thank you for your exhibition. I want to talk a little bit about the problems that dark matter have along the whole spectrum of phenomena. Yes, and how come? I mean, they're still missing a lot of phenomena that dark matter cannot explain, like globular clusters and enanas spheroidales, spheroid dwarfs, and extended binaries, which I think the lowest, the smallest systems that present this phenomena, and where dark matter has absolutely no way to explain.
Yeah. Yes. You want me to comment on this? Yeah.
Yes. Yes.
Yeah. So, right. So there's the dark matter camp, which is quite big, and then the smaller modified gravity camp. And I find it socially or sociologically very interesting how they interact with each other. So both of them are really convinced that their paradigm explains everything and are somewhat blind to their weaknesses. I think dark matter has a lot of successes, but also lots of problems, and sometimes these are swept under the rug. Especially these happen at the small scales, and then typically the answer is, oh, that's gastrophysics, that's just lots of tiny feedback, lots of parameters, we'll fix that, but that's messy, so it doesn't really count as evidence in favor or against. And then the modified gravity people will say, that's where we shine, right? They can explain the Tully-Fisher relationship and mass discrepancy acceleration relationship and many other correlations, which I don't think dark matter can, and they tend to ignore those pieces of data. So I think both of them have strength, both of them have weaknesses, and I think it would be a win-win situation if all of them are better at listening to the others. And I think the examples you mentioned are definitely worth listening to, and I don't think they're listened to enough.
Okay, Niels, I have a question. In the context that you showed the anti-realism tree and your vision, and taking into account the vision of Peebles, of Jim Peebles, that he said that probably, given that we are made of baryons and we live in a baryonic context, probably it could be for us all these candidates have different interactions with the baryonic components, and perhaps we can perhaps to face the problem that we will never be able to detect, even though the candidates are producing observables and interactions with baryons and with observable matter, but only in the gravity way. So how do you classify that kind of candidates and the kind of interactions in the realism tree?
Okay, I'm not sure I fully understood the question, but I think I want to say that indeed one of the reasons why this semantic common core is so thin is because, if I understand you correctly, you're saying we might never have anything other than gravity-mediated evidence, and I think that indeed feeds into the idea that this common core might never be narrowed down enough. So then it seems you would be, because of this semantic problem, you're epistemological anti-realist. I don't think the race is done yet, so I'm trying to stay optimistic. But yeah, there's no guarantee we're going to narrow this down for the reasons you spelled out. Yeah.
Okay. Thanks. Okay. Thanks, Niels.
Thank you.
Green. Can you hear us?
Yes, I can hear you. Can you hear me as well?
Okay.
I will try to share my slides. Okay, can you see my slides without any notes or anything?
Just a moment. Okay, yes. There we have your presentation. Okay.
Okay. Should I start?
Yes, please go ahead.
Okay. Okay. Hello, everyone. I will talk to you today about black holes and the idea that we can understand them as massive space-times. So I work on this topic together with Niels Martens, who you just listened to. And we look into this topic in the context of the distinction between space-time and matter. And I think that black holes can teach us very interesting things about this distinction. So I'll first say a bit more about this distinction between space-time and matter. Then I'll introduce 5 different ways of interpreting Schwarzschild black hole mass. I'll focus on one of them in particular then and motivate that even though it's a bit of a weird interpretation, we should really take it into account when we try to understand black hole mass. And then I'll come back to the distinction between space-time and matter and say what these interpretations imply for that distinction. So traditionally, we have assumed that everything falls in either of these two categories. So something is either space-time or it is matter. But this is not very clear when you look at modern physics, in particular modern cosmology. And in 2020, Niels Martens and Dennis Leemkool published a paper on this. They focused on dark matter. And they came up with 2 lists of criteria, one for when something is space-time and one for when something is matter. And what I will do in this presentation is discuss what Schwarzschild black holes can teach us about the distinction between these 2 categories, and if we should really hold on to this distinction, or maybe it serves us better to let loose of understanding these 2 concepts as very distinct. I will go into this question by focusing specifically on 2 matter criteria. So usually we think that matter possesses energy or has a rest mass. And we can subdivide these criteria into 3 more specific ones, namely that This energy or this mass is representable by a stress energy tensor. It's ascribable to each point in space-time, or it's ascribable to a particular space-time volume. And what I will do is I will argue that the criteria of possessing energy and rest mass suggest that the strict dichotomy between space-time and matter breaks down in the context of a Schwarzschild black hole. So in order to look into this, it's important to really understand what it means to have mass or to be massive, and what it means for a black hole to have mass or to be massive. And I will focus on one particular type of black hole, namely the black hole that's described by a Schwarzschild solution. And this is a static spherically symmetric vacuum solution to the Einstein field equations of general relativity. And it's described by the metric that you see here. Let me check if I can find a pointer. So this m that we see here, we usually take that parameter to be the mass parameter. So one way of formulating our question is what justifies really interpreting this m as a mass. So part of the difficulty in answering the question, what does black hole mass mean, lies in the fact that our intuitions on the concept of mass are still very much rooted in a Newtonian theory of gravity. But it's not clear how this Newtonian conception of mass transfers to the general relativistic regime. And it's also not clear what it means for a black hole to have this property of mass. So one thing that complicates understanding this is that it's also not even really clear what a black hole is, or at least you can understand it as many different things, as Eric Curio also wrote down in a paper from 2019. Another striking fact of characteristic of black holes is that they are described by vacuum solutions. So there are no matter field presence, yet they do have a mass. So the question is, how is that possible? So our aim was to find a notion of mass that is still sufficiently similar to the Newtonian conception of mass, such that it also has this epistemic value, but that it also accurately describes a property of a Schwarzschild black hole in general relativity. And because this is such a complicated aim, we feel that it's best conceptualized by using a multiple modeling approach. So this is familiar in physics, where very complex phenomena or such as QCD are investigated by using multiple models. And this allows you to get more knowledge of the same system than you can get when you use only one model. One question that's important to ask then is if each of these interpretations indeed refers to the mass of a Schwarzschild black hole. So should we really take into account all these interpretations when we try to understand what it means for a black hole to have mass? So in order to answer the question, let me quickly go over these different interpretations. So first, here at the top, the Newtonian trickle-down interpretation. This interpretation holds that in the weak field regime of a Schwarzschild metric, the behavior of a test particle is approximated by the behavior of a test body in Newtonian gravitational fields sourced by a mass with the same numerical value. Then we have the point particle idealization interpretation. This is a special relativistic interpretation. And this reflects the idea that you can zoom out of the space-time very far and then treat the Schwarzschild black hole as if it is a point particle living in Minkowski space. And as such, it has a form-factor from which you then determine the mass of this point particle, so of the black hole. Then we have the assembly interpretation. This justifies that a black hole or Schwarzschild black hole has a mass because we know that black holes can be created by basically throwing a lot of massive things at a point. So here, this notion of mass is really a Newtonian notion of mass. Then at the top left, we have the singularity interpretation. And this is an interpretation that kind of postpones really thinking about what black hole mass means to a different theory. So, for example, it says that when the singularity is resolved in a quantum theory of gravity, then this new quantum theory of gravity will also tell us how we should understand the mass of this black hole. And then the last one, which is the one I will talk about most in this presentation, that's the global interpretation. And this interpretation is formulated within the framework of general relativity. And it states that mass is a geometric quantity that's attributed to the spatial temporally extended region containing the black hole or identified with the black hole. So this global interpretation is interesting because it's the only interpretation that does not reflect the traditional view that mass is a local property. So it's in this case particularly important to really ask the question, why should we take this as a mass and why should we take this into account when we try to understand what it means for a black hole to have mass? So does the global interpretation really refer to the mass of a Schwarzschild black hole? So that is the question that I will try to answer in the next couple of slides. So as I said, the global interpretation is formulated entirely within the formulation of general relativity. And you can kind of see it as a response to the fact that there's no straightforward frame-independent way to give a local definition of energy momentum in general relativity. So instead of going for a local definition, you go for a global definition of mass. And what you then get is that you get a geometric boundary quantity that's attributed to a spatially or spatio-temporally extended region that contains the black hole. So to see why this is still a valid notion of mass, even though it's global, I want to say a little bit about this specific example of a global notion, namely the Arnold-Dazer-Misner mass. This was introduced in the 1960s within the Hamiltonian formulation of general relativity. And it gives this equation as defining a notion of mass. So what's interesting from this equation is that you can see that it's a geometrical notion of mass. And I will come back to this also when I talk about the space-time matter dichotomy. And we see that it gives a deviation from flatness that's measured by the metric. So it is an integral over the boundary of a spatial slice. And this is a derivative of the induced metric on that spatial slice. So how do we arrive at this equation? I think the process can be summarized as that you introduce a background structure in the Hamiltonian formalism of general relativity, such that two specific physical principles apply, namely that of conservation of energy and that of Lorentz invariance. And it's interesting to note that this is very similar to the point-particle idealization interpretation, where we understand the black hole to be, that it can be idealized as a point particle that then has a 4 factor that gives you a mass. The same holds in this case. This mass is the result of attributing a 4 factor to the space-time, from which you can then compute the mass. And I think it's these two physical principles that provide good reasons for us to believe that the global interpretation does refer to the mass of a Schwarzschild black hole, even though it's weird in the sense that it's not a local notion like all the others and like the Newtonian conception of mass, but it's a global notion. So if we take this global mass interpretation as a valid interpretation for the mass of a Schwarzschild spacetime, what does that then imply for the ontological status of spacetime and matter? So I first want to look at this global interpretation again, and then I'll compare it to the other interpretations that I introduced. So I want to discuss this question: what position should we adopt regarding the ontological status of space-time within the context of the debate between the relationalists and the substantivalists? So here I gave 3 very short summaries of these various positions, and I took them from a paper by Dennis Leemkoop. So relationalism holds that matter is the only kind of fundamental substance, and that space and time are just abstractions of or derived from material bodies. Then substantivalism is the view that space-time is a substance in its own right. So matter can also be a substance, but at least space-time is also a substance, and it might also be the more fundamental substance. Then there's super-substantivalism, and this is a view that's, I think, a little bit less well-known. And it holds that space-time is the only kind of fundamental substance, and matter is identified with or constructed out of space-time. So let's see what the global interpretation says on this, what position it suggests that we should take. For this, I first want to go back to these matter criteria that I introduced. And I want to see if these apply to the global interpretation, such that we can use a global mass, for example, the ADM mass, to identify something as matter. So the ADM mass fails to satisfy the strict criteria of being representable by a stress energy tensor and being ascribable to each point in space-time. But as a global notion, it does satisfy the criterion of being ascribable to a particular space-time volume. And therefore, we can say that there's a weak sense in which a Schwarzschild black hole is both space-time and matter. And so we can already see that at this level that there's a conceptual breakdown of the dichotomy between space-time and matter, because in this case, they are both the same things. A Schwarzschild black hole is both of these things. So what does that suggest for this debate between the relationalists, substantivalists, and super substantivalists? I think that this suggests that we should take a super substantivalist position, because it says that space-time is identified with matter. So coming back now to the other interpretations, we also analyzed what these interpretations suggest on this debate, and this was our answer to this. So I don't want to discuss every position in detail now, but I do want to point out that well, it's clear that none of these, all of these blobs do not have the same color. So we have different colors in this diagram. And that's very interesting, because it means that it depends on which interpretation you take, what you should think on the ontological status between space-time and matter. So we have a contradiction here. So what does it imply? How should we respond to this contradiction? What we could do is say it's not really a problem. Let's embrace the contradiction. So you could do that by taking a perspectival realist stance, or you could take a more firm approach in a sense and say, well, it's okay that all these positions have different metaphysical implications, because well, ontological pluralism solves this contradiction. It's okay to have multiple ontologies. We can also work towards avoiding the contradiction, and for example say, well, scientific progress will show us that out of all of these interpretations, one is really superior. So where we claim that we should really take into account all these interpretations to understand black hole mass, someone who would go for this argument would say, well, maybe now, but in the future, when science has progressed more, it will become clear which interpretation we should favor, and then we can also favor the metaphysical implications of that interpretation. And then there's no contradiction anymore. And then the last solution is to say, well, okay, What we could also do is just say that this distinction between space-time and matter that we have held on to for so long just does not make sense anymore in the context of a Schwarzschild black hole. So we have a metaphysical breakdown of the distinction between space-time and matter. So a short summary of what I talked about. I have argued that black hole mass is best conceptualized by considering multiple interpretations. And I've shown that the global mass interpretation implies a breakdown of the space-time matter distinction in two ways, namely in a conceptual way, by showing that a Schwarzschild black hole can be understood as both space-time and matter, but also in a metaphysical way, because it contradicts the other interpretation of mass on the ontological status of space-time with respect to matter. And I've included some references.
Okay, thank you, Sen. So, and for questions?
Hi. Thanks for the talk. Do you hear me?
Yes, I hear you.
I would like just a question, a small question. In your ontology of space-time, or your approach to the ontology of this topic, in which place you put quantum field theory, especially all the branches related to a kind of notion of a space-time, right? Because Arnold Esser-Misner is a line, right? Okay, you go to Newtonian, etc. But it seems to me that from the point of view of quantum field theory, there are new approaches, obviously speculative, like Arkani Hamed, for instance, I suppose you know, from Princeton, in which sense space-time is an approximate notion, not really a kind of ontology based in general relativity. So it seems to me that in a way, we have to divide with kind of theoretical approach we use to go to this direction of ontology or metaphysical approach. I would like to know your opinion, nothing else. Thanks.
Yeah, that's an interesting question, I think. I think what your conclusion is on this distinction between space-time and matter could also rely on which case study you look at. So within the project that I work, there's also Antonio, who's also going to present after me, for example, works on inflation. And you can also look at dark matter and dark energy like Niels does. And I think, for example, dualities like holography in quantum field theory could also be an interesting case study to see if this dichotomy holds up. And then for one way to approach it could indeed be to say, well, space-time is made up from matter because it might be emergent, because it emerges from CFT or from a quantum field theory. I personally do not know enough about that topic to really say if I would agree with that, but it's definitely an interesting thing to think about also in this context.
Okay, next question.
Hi, thank you for your talk. My question is, in your analysis, the Schwarzschild solution of the general relativity equations is not an object, it's a theoretical solution to a theoretical model in a very simplified situation. In which way this affects you, the position of this analysis as a proof or indicious in some way or another in the case of ontology of the real world?
Yeah, so I think this is a problem that's very common when you analyze very theoretical things. And I think black holes are in many ways very theoretical things, that there is this gap between what the theory tells you that the thing is and what the thing might actually be. So I do think that even though it's a highly idealized solution, it's very symmetric, and there's also no spin or charge in the case of a black hole, a Schwarzschild black hole. It does gives you some direction into thinking about what an actual black hole might be. So it doesn't say nothing about it, but of course, a Schwarzschild black hole is not exactly what we think is out there. So yeah, it gives you some direction of what to think about, I think.
More questions.
Hello, my question is whether you endorse the super substantivalism. Because it reminds me an old abandoned program by John Wheeler, the geometry of dynamics, in which all there is space-time, but that program fronted the difficulty to explain the enormous diversity of particles we have discovered and to which we attribute mass. Not just black holes, but we attribute mass to a whole variety of particles, and it seems for that kind of program and difficult to account for that phenomenon.
Yeah, I think I always use Wheeler's program as the example to explain what supersubstantivalism is. So yeah, I think it's definitely the best way to think about how supersubstantivalism could work. If I myself think that's the way the world is, I don't know, but I do think I try to show that within general relativity there is a way to understand black holes, the ontology of black holes, as supersubstantivalist. If you really think that this general relativity way of defining mass, this global way of defining mass, is the right way of defining mass, then I think you're taking a supersubstantivalist position. Yeah, but I would do that. I think we should take all of these interpretations into account. So, yeah.
Let's thank Zane again.
Thanks for the questions.
Okay, Antonio, could you share your screen? So.
Yes.
Okay, so this is Antonio, and okay, you can see the talk. So,
yes, thank you. Can you see my screen fully?
No, we see the I mean, not the full screen. Lens.
Okay.
See,
Wait.
I think I shared it as screen and not as.
Yeah, I will try to also do that. Now you see?
Yes, yeah, we see it.
Okay, great.
So you're going to in English, right?
Yes, I will do it in English, although I accept questions in Spanish also. Yeah, I'm sorry. I would have to translate a lot of technicalities to Spanish, and that would probably take me more time. Perfect. So excuse me, but I will do it in English. Yeah.
So go ahead.
Okay. So thank you. Yes, I will be talking about a work I've been doing with Alex Fleuren. Hopefully it's almost finished work. We will soon try to submit something, and I hope you all stay tuned, because even though you may not agree with what I'm going to say now, we try to really do a good overview of the program of inflationary cosmology in the last 25 years. And I think we try to be as complete as possible. So I think it could be useful, even though you may not agree with the conclusions we got from this analysis. So let me just skip directly to the conclusions to make you think, well, how I think about inflation. So inflation, the research program of inflationary cosmology started as a solution for fine-tuning puzzles. and has survived the cosmology revolution of lambda CDM and precision cosmology era. But in the current state of art, it should not be considered as an independent dynamical theory, but rather as a cosmological lab or as a kind of ruler that would potentially become a bridge between new theories and cosmological observations. So I will now try to argue in favor of this position, and hopefully you can comment if you agree or disagree. So let me just briefly introduce a bit of cosmology required to understand inflation. So we can divide, in my opinion, cosmology, at least for our purposes, as the pre-lambda CDM epoch and then the lambda CDM epoch. So the pre-lambda CDM epoch, so before 1999, more or less, it gave us a lot of information about cosmology, mostly about the CMB. And here in the slides, you can see two pictures of the CMB. The first picture, which was the first original picture of the cosmic microwave background by Penzias and Wilson in 1965, provided evidence that we live in a universe that is expanding, and which means that if we go back in time, we have a very hot plasma of interacting photons and atoms, and by understanding the physics of this hot plasma, which we understood because we had already a good understanding of that physics from laboratory physics, we could then explain why do we see this black body radiation of photons that were produced by this epoch known as recombination era. And then on the right-hand side, we have a better picture of the CMB by the COBE telescope, which not only supported again that view of the Big Bang model, obviously, but also provided a fine account of the temperature of that black body. But for us, for my talk, most importantly, it provided evidence that there were tiny anisotropies of the order of 10 to the minus 5 in terms of amplitude. Now, where does inflation come to play? Well, it basically it was proposed in between these two observations in the 80s, and the idea of inflation is that before the Big Bang, as understood as this kind of hot plasma radiation atomic interaction, before that there was another phase of accelerated expansion, or what we call the de Sitter expansion, and what this helps is to what is called to solve some fine-tuning problems that were already being discussed during the first evidence of the cosmic microwave background, and it had to do with the fact that we observed the CMB very homogeneous, and also we observed that the space is almost flat, and this kind of explanation would require some fine-tuning, but inflation would provide a natural way of solving this without this fine-tuning. But for me, most importantly, is that some years later, but even before COBE, there was the evidence that inflation would not only solve these fine-tuning problems, but also provide anisotropies, the mechanism to these anisotropies that then later were measured. Okay, and most surprisingly, for of course for the theoretical enterprise, was that they have to do with quantum physics associated with inflation. Now, coming now to the lambda CDM era, I marked the lambda CDM era between 1999 and 2004, coming from Peebles' book, where he really emphasized, and I think it's also very important to emphasize, that the lambda CDM model and precision cosmology have been marked as a revolution in cosmology, in a different way of thinking about the universe as it was prior to that. And so basically the lambda CDM model is a theoretical model. I can show you here. Is a hybrid framework composed by some known theory of gravity and matter. We use general relativity, we use atomic physics, we use thermodynamics, hydrodynamics, many different branches of physics that are well understood in their domain, plus some phenomenological models, and you have already heard about dark energy and dark matter, plus the primordial power spectrum, which I will comment now. And basically, what we do with this theory plus phenomenological models is to create a full model, the lambda CDM model, which has some 6 free parameters. Okay, and on the right hand side you can see the paradigmatic plot where you can see how impressive this revolution has been, because we have on one hand the lambda CDM model, which is the gray line that fits perfectly the data, which is precision cosmology, in the sense that we have very precise measurements, and they fit surprisingly well. And what we are measuring here is what is called the correlation functions, which measure the difference of temperature between 2 points of the CMB that you see on the left-hand side, measured in this case by WMAP. Now, for us, the important thing is that inflation does play an important role in lambda CDM, because it basically explains the initial conditions. Okay, it provides an explanation of the primordial power spectrum, and in terms of the parameters, it should explain why we have these parameters AS and NS, which have to do with the amplitude and the spectral index of the primordial power spectrum. But before going into inflation, I want to say another thing, and is that although we do have a lambda CDM model that, again, has well understood physics underlying it and some phenomenological models, it is true that actually none of these 6 parameters are well understood physics. Both omega lambda and omega c, which is the energy density of what we call dark energy or dark matter, as Niels showed, does not have a clear explanation yet. But even omega matter, because omega matter, the fact that it's different to 0 has to do with the fact that there has to be some mechanism that provides what is called baryogenesis in order to have not a 0 magnitude for this omega matter, because from theory, from a theoretical point of view, we would expect that there is some kind of symmetry between antimatter and matter, and why this is not the case has still to be explained. In a similar manner, also tau has to do with ionization, which we also don't understand. And finally, AS and NS have to do with inflation, but as I will show, it's still very unclear exactly how this explanation goes. Which, a good thing in this sense, means that we can think of lambda CDM not just a kind of historical explanation of the evolution of the large-scale structure, but actually as a way of testing, or at least to provide new evidence for physics, for new theories of gravity and matter. And then the question is how inflation participates in these 2 functions. So let me go back to the cosmic microwave background. So if we want to explain this very famous plot, we need at least very briefly 2 ingredients. Okay, we need to model first what is called the primordial power spectrum, and it's usually modeled in what I call the almost horizontal Dovik model, which this is in principle a phenomenological model that inflation would provide the explanation for. As you see, even though it has logarithms, it is actually a very simple model, and it works perfectly to fit the data. But obviously, we don't only measure the primordial power spectrum, the original anisotropies caused by inflation, but we measure the full angular power spectrum. And this power spectrum includes also a contribution that is usually in this sigma function that you see there. Sorry, that is called the transfer function. And this transfer function basically includes all the physics that goes from after inflation finishes to the formation of the CMB, and then from the CMB to until we observe it today. And this is a very detailed account of a lot of physics going on there, but the important point that I want to make is that the dynamics that is going on there in this transfer function is required to understand the angular power spectrum. We cannot model this transfer function in a very simple way, as we can do, for example, with the primordial power spectrum, in order to, for example, show that there are peaks. If you see in the plot, there are some important peaks, and we need to really know the dynamics of the physics of recombination. We need to do approximations, we need to know how matter interacts, and there is a lot of physics going on. Then compared to the case of inflation, of how inflation provides this primordial power spectrum, is completely different, because in the case of inflation, it only provides the initial seeds and it can be modeled in a simple way. And inflation only provides, let's say, the two parameters, AS and NS, that are then modeled. Whereas the other physics that enters the recombination, which is where the other magnitudes appear, like omega baryonic, omega cold dark matter, omega lambda, tau, all these other parameters, they appear in the full dynamics that we require to explain the CMB. So the first conclusion is then that inflation does only provide the required parameters for the almost horizontal double power spectrum. We don't require the evolution dynamics. It just provides the initial conditions, meaning that in at least in the way we see cosmology today, in the terms of lambda CDM, we don't have any way of knowing the exact dynamics of inflation, because it just doesn't appear in the equations we require to fit the models with the data. Okay, so in this sense, I hope briefly I could respond the first question. What is the role of inflation in describing the history of evolution of the large-scale structure? As I say, inflation would only provide the initial conditions, but would not provide dynamics, a dynamical account that is required to lambda CDM, because lambda CDM does not require you to know the details of the dynamics of inflation. Now, for the second question, what can we learn from inflation as a possible test of new theories? I will have to briefly explain the traditional way of thinking about inflation in terms of a scalar and a potential. We can think of as the plot you see on the right hand side. So in this way, we think about inflation rolling down the potential, and this potential energy creates the accelerated phase, the classical expansion that we need, and then small fluctuations of this scalar field, when they are then quantized, provide then the anisotropies. And then finally, we need, of course, to explain why we don't see inflaton particles in the universe, but we see actually the standard model of particles in the universe. And so we need a mechanism, which is called reheating, that transfers the energy from the scalar field to the standard model particles. Okay, so this is a very, 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 very brief explanation of inflation. Obviously, there are books that explain this in detail, but hopefully the idea is clear. And for me, the most important thing is that the way we connect with observations is that inflation, on one hand, provides you an explanation of why the NS, the scalar, the scalar, I forgot the name. Well, NS is almost near to 1. And second important thing is that inflation also provides you tensor perturbations, okay, by a similar mechanism. And then one can measure this parameter R, which is the tensor to scalar ratio. And just basically, you just need to provide to me the potential. And then I can tell you how these two parameters, the value these two parameters have. And we have very good, both the value, we have the value of NS, of a very good precision, and also a good constraint on R, which then allows us to compare different models and see if they are favorite or disfavorite. And then you would actually say, well, this looks pretty much like basically you are doing here almost like particle physics. You know, we are having different candidates of theories, and then we show in the plot the data, and we see, okay, which one is better model, which fits better, and so on. Now, the problem for this is that actually once you try to say, okay, how many possible models do I have, you come with the fact that there are too many to really do a proper analysis. And actually, I mean, people have done a statistical analysis of which ones is the preferred models and so on. They come up with different way of measuring if a model is favorite or not. And then you can see in the right hand plot that there are many models that are favorite, and you can come up with whichever model you want with the parameters you need, and then you can fit the data. Now, this is usually what is called the underdetermination problem. And the conclusions we get is that this is not only a problem now, but it seems, at least from the eyes of lambda CDM, of course this could change and we could have a new cosmological revolution in the near future. But now, as we see in the lambda CDM, this won't change in the near future. So it's very difficult that we can get lambda CDM to provide us insight of saying, okay, only one model will ever survive, because you can always fit it and accommodate the data. And the second point, which I think it's also as important, is that almost all these models, they come from underlying proposals of theories that go way beyond the theories we understand now. So you remember, like I said, in lambda CDM, we have general relativity, thermodynamics, particle physics, but these are well-known physics in the lab, and then we extrapolate it to cosmology. For inflation, the problem comes is that most of these theories, they come either from string theory, supergravity, modified gravity models, and the control we have of these theories are very not very good for now. And you can actually, even with one framework like string theory, you can propose many types of potentials, and choosing which of these potentials is the right one is still something we have not yet understood. So from this both positions, it seems that this strategy cannot be very successful in the near future. And a second point, I have to really quickly explain it, is that new data is coming, and it's hindering this program even more. So on one hand, in the left-hand side, you can see a plot. The gray line is what is called the Starobinsky model, which is the most favorite model of Planck data, the CMB Planck data, which you can see in red. But then once we have other types of measurements, for example, also the cosmic microwave background, but coming from the Atacama telescope, which measures different distance of the correlation functions, we see that actually Starobinsky is not so favored. So new data is coming, and of course this way of saying, oh, this is more favored, this is disfavored, is highly dependent also on the instrument we are using, or at least that's what data is telling us. And what is furthermore even more dramatic is that new data is also favoring different accounts for the lambda CDM model. We have, for example, the problem of the Hubble tension, which is still an important issue in the lambda CDM model. And people have come up with new ways of solving this Hubble tension, meaning that the Hubble constant that you measure in the CMB and the one you measure from supernova, to put them together. And by putting them together, you can come up with new candidates of dark energy, early dark energy, for instance. But the problem with it is that dark energy, because the lambda CDM depends on the dynamic of dark energy, it will also affect then the NS parameter. And of course, then it will change the way inflation participates in, what inflation predicts to this NS. So in this plot, you can see in the medium plot, you can see how by changing the model of dark energy to go to the Hubble constant to 73 almost, you change the spectral index. Sorry, the spectral index. And by that, you can also then change if the models of inflation are favored or not. So what I mean here is that new data and new models and lambda CDM and possible alternatives that could in principle be possible could even distort more this program of selecting which potential fits the data. So let me here then just conclude. Lambda CDM cannot provide evidence for a dynamical theory of inflation. It only provides constraints for some parameters and favors simpler inflationary models. So then we can ask the question, are we done here? So is this the end of inflation? Can we not do anything further, right? And then our answer is no. Actually, we can go further, and it has to do because inflation is a new phase that we add to the Big Bang model. We can actually use this not as an explanation in itself, but actually as a laboratory in itself, and try to provide new models and new theories that happen during inflation, not something that produced inflation, but actually physics that happened during inflation, and see if then we can actually observe new data that is evidence for this new physics. And I will briefly show you two options here that are very promising. One is what is called non-Gaussianities, and another is the stochastic gravitational wave background. So, sorry. So what is non-Gaussianities, very briefly, is that for now we measure that this primordial power spectrum is what is called Gaussian. The distributions of these anisotropies are Gaussian, but it could be possible that measuring more precisely these anisotropies, it happens to be that they are non-Gaussian, and we can measure these non-Gaussianities from the CMB if we are precise enough. And then there are two possibilities that these non-Gaussianities could appear. One, for example, is the loop quantum gravity, which is a quantum gravity program. If you do the version for cosmology, which is called loop quantum cosmology, then this program forces not a big bang, but actually a big bounce, where you have not a singularity, and this big bounce would then produce these non-Gaussianities. But the important thing here is that they are produced because there is inflation. So inflation, let's say, stretches these consequences, and we could, in principle, if we are precise enough, observe the very, very early universe, this big bounce, just by measuring these non-Gaussianities. A similar program is being carried on, and it's very growing, let's say, which is what's called the cosmological bootstrap. Has to do with the fact that string theory proposes a lot of degrees of new degrees of freedom, many new degrees of freedom, scalar fields that are heavy and light particles and so on. And so the question here is inflation has happened, and there are many degrees of freedom. Can we observe them? And there's this whole industry to compute these things, and using the Sitter spacetime and using inflation, one has a very, very good tools to analytically compute them, and in principle produce these non-Gaussianities that eventually, if we will be able to measure it, then could provide evidence for these new degrees of freedom proposed by string theory. And lastly, very quickly, we know that gravitational waves exist. We have detected them, and then the future is very bright for gravitational waves. We will have soon, let's say in 10, 15, 20 years, LISA. And the consensus is that LISA has enough precision, and the frequency band is the one that it is, so that we can measure effects that happened during inflation. And the important thing is that LISA will not measure gravitational waves produced by inflation, like the tensor perturbations. It's not able to measure that, but it's actually being able to measure possible physics that happened during inflation. And two things are here important. For example, phase transitions could be important, and also the phase of reheating. So I told you that there is this phase between inflation and the standard model, and we would like to know about this. And this reheating processes of how this happened produces gravitational waves, and in principle you could measure that by LISA. And there's this paper by Caprini and Figueroa where they explain how this is possible. Okay, so let me just conclude here. So inflation provides a robust mechanism for generating the initial conditions of the early universe. Current observation indicates that it's almost scale invariant primordial power spectrum, and it's remarkable agreement with the prediction of single scalar field inflationary models. So that's what we have learned from lambda CDM, and that's why people are very happy with inflation. Now, what is the next step? What do we do now? Well, in our current understanding of cosmology, for now, what we understand about lambda CDM is that we can assess the dynamics that underlies inflation. And then I do this comparison to similar to how we can assess the dynamics of rods and clocks in special relativity without electromagnetism or quantum mechanics. So the idea here is that inflation would require, in principle, a dynamical theory, but inflation as an independent dynamical theory is not clear. We don't have enough evidence for that. So we need to wait until in the very, very, very far future, we can understand the full dynamics. But that doesn't mean that the program should be stopped, at least for now, because it serves as a laboratory for new theories of quantum matter and gravity, similar to special relativity, how it also served historically. And the expectations are considerable, detecting non-Gaussianity, stochastic gravitational background, and so on. And then we also argue that if we would not detect any consequences of that, which could be the case in the future, then of course this would diminish the program of inflation. And then what we compare it to is actually to the program of baryogenesis, this matter-antimatter asymmetry, which also historically was very, people were very excited at the beginning, but then it just hasn't progressed enough to become a program for the lambda CDM. So I will just stop here and accepting your questions, and both in English and Spanish. Thank you.
Okay, thank you. Thank you.
Yes, thank you. How do you think the non-detection or of the inflaton, the particle that would get the inflation going, affects the credibility on this theory?
Yeah, thank you. So good question. I mean, I think since the beginning, people already assumed that we will not be able to detect this inflaton because the energy scales to produce it are too high. Now, people at the beginning, historically, they expected that maybe some underlying mechanism, like some symmetry breaking of ground unification theories that maybe we understand could provide inflation, but then this became also not possible, and then people proposed the scalar field, and so the hope would rather be to detect some kind of imprint that this inflaton left, but not the inflaton in itself. So I think from the start on, you assume that this will not be possible, and then, as I say, you just hope that inflation can provide you new insights of other kinds of theories that can make progress. So the question we ask in this work was not so much if inflation is worthy to pursue or is very good. It's just what is been done and what is the progress of inflation. So will inflation be still a good research program now and in the future? And that's the type of question. But of course, I agree with you that if you are very strict compared to like particle physics, then of course this doesn't have any new avenue. Yeah.
Hey, hello. Hi. You hear me?
Yes.
I remember a time when Google, for example, appeared in the scene, and a lot of articles and people worked on the scenario of inflation, right? So after that, many philosophers enter into the game, but just thinking that probably it was a very good tool for crossing from explanation to prediction, right? Probably you don't say it's the best explanation, maybe it's the only explanation, right? At that time, I'm talking several decades ago. My question to you is, in which way you think that this is the same tool, or in which way prediction is advancing in this direction of the standard cosmology, let's say? Do you understand my question?
No, maybe can you elaborate a bit more?
It seems to me that in cosmology you mentioned in your talk quantum cosmology, all Vilenkin, all this Lind, etc. All the transition from the first 3 minutes to the first 3 seconds to the etc. Right? When you finish with the standard model, let's say general relativity model in cosmology, and enter into a kind of mixture between classical and quantum analysis of cosmology, and in which way you use this as a tool for trying to take the standard tradition of going from general relativity and cosmology to the early stage on the universe, right? So this is a break that at last at the level that I know the topic is not in a way connected. It's a break between classical cosmology and quantum cosmology.
Yes, I mean, maybe I can say something and then you tell me if it has to do. I think historically the dream, let's say initially, was that there would be a smooth transition, like particle physics would be very smoothly extrapolate to cosmology, and we would be able to understand, let's say, this quantum, this QCD, or like good transitions in the early universe, and this would be beautiful. We could then detect it in the CMB, and these two fields would merge very beautifully together. But I think this has not been fulfilled. But not even for inflation and for many other topics like dark energy and so on. It seems like it's tricky to do so. And then the next step, of course, was to say, okay, if this part beyond particle physics, but still normal particle physics, is not successful, then let's go to quantum gravity. And then, of course, the biggest candidate to pursue this was string theory with the ideas of potentials. But then, of course, this becomes trickier, in my opinion, because you are using cosmology to test theories, but cosmology for now has not been able to test any theory beyond gravity. So I think then the epistemology, like the strategy there, the scientific program will be different, of course. And I'm not sure if I can say if it's good or bad, but yeah. So I don't know if that I understood, if that was what you had in mind or something else. Yeah, sorry, I cannot hear.
Several different models, right? So from the point of view of epistemology or people interested in analyzing scientific activities, it's not always very easy to enter into these different models to try to connect them. People use literature, for instance, consistent theories, coherent theories, and all that. But, well, for some people, for philosophy, it's not enough, this kind of between one conceptual field and another conceptual field, right?
Yeah.
The question.
Yeah. So actually, I mean, one of the other critiques that we have proposed in the paper is that I think people had in mind this way of all these candidates for inflation, just plot them, and it would be similar as I remember, like this particle zoo, right? You would have a detector and you would measure a lot of particles. You say, if I add this mass and this spin. But I think this is two totally different strategies, because on the particle physics side, you have an underlying framework, which is quantum field theory. You can apply it, and then you can say, maybe I have this model or this model, but they are unified in this framework of quantum field theory. Whereas in inflation, it's true that some of these models, they come from very different frameworks and mechanisms that come from, as I say, string theory, supergravity. But it's not clear even in string theory if there is a unique way of proposing this. So different people have different ways. So it's very difficult to say that this would be a successful way of it's just a detector. We like some kind of detector that we will say, the inflaton has this and these properties. I think it's you need to either you accept the fact that this is the only way possible for now, but obviously don't try. I guess that if there is something to learn, is that you cannot compare it with, let's say, the successes that particle physics had during the last century.
We have no more time, so let's thank all the speakers.
Un aviso para los presentes: a las 2:15, no en streaming, sino solo tenemos una avant-premiere sobre el documental de Thomas Kuhn, que se filmó en Uruguay, así que están cordialmente invitados. Dura 1:05 aquí, lo pasamos 2:15, así que podemos comer y venir un poco más rápido para no alterar el programa y poder aprovechar que tenemos